Alright, so we're going to be looking at 8.1, which is function tables on pages 579 through 582. So if you could please open up to those pages now. Alright, the real world link says ruby-throated hummingbird beats its wings about 52 beats per second. And they want you to fill in the tables below with information. So the first one, for example, it says make a table showing how many times this bird beats its wings in 2 seconds. So it's saying the number of seconds here, and then it's going to be S times 52, S standing for how many seconds the bird is flapping its wings, and that it's 52 wings per second. So we're going to substitute in for seconds that it's 2 seconds long, and we're going to multiply 2 times 52. And then that's where we fill in how many beats per second. So go ahead and fill that in, and then carry on and do 2, 3, and 4 on your own, and when you come back, we'll have the answers. Pause now. Okay, and here are the answers. That in 2 seconds, it beats its wings 104 times. In 6 seconds, it would be 312 times. In 20 seconds, it would be 1,040 times. And then in 4, it says that we're talking about a giant hummingbird, and that it beats its wings about 10 times per second, and we want to know how many times it beats its wing in 3 seconds, and so that would be 30 in this case. Alright, so it says that to find the output for a function table, let's review some vocabulary. A function is a relation that assigns exactly one output value to one input value, and the number of wing beats, which is the output, depends on how many seconds that we have, which is our input. So of course we wouldn't know how many times the wing beats if we didn't know how many seconds there were. So the output is reliant on the input. So the function rule describes what relationship is going on between each the input and output. You can organize the input-output tables and the function rule in a function table. In a function, the input value is also known as the independent variable, since it can be any number you choose. And the value of the output depends upon the input value. So, depending on how many seconds I said that the hummingbird beats its wings, depending on the seconds is how many times it beats its wings. So, its independent is the amount of time, and the amount of times that it beats its wings is a dependent variable, which is the output. Alright, so for number 1, it says the output is 5 more than the input, or sorry, 7 more than the input, which is like saying x plus 7, because we know input is x, right? And output is our y. And we'll talk about that in just a moment. It says complete the function table for this relation. So the function rule is x plus 7. We're going to add 7 to each input. So we've got the input is 10, so we're going to do 10 plus 7, which is 17. If the input is 12, then the output's 19. If the input is 14, then the output is 21, because we're adding 7 each time. And so that's what this represents. So example number 2, it says that the output is 5 times the input. Complete a function table for this relation. So it shows us that the function rule is 5 times x, where we're going to multiply each of the inputs times 5. So for the first one, we're going to have 5 times 8, which is going to be our 40. Then we're going to do 5 times 10, which is 50. And then we're going to do 5 times 12, and we get the answer as 60. And so we know that our rule is times 5, and for each one, we're going to take whatever the input is, and we're going to multiply that times 5. Alright, now you're going to work on the 2a and b on your own. Notice that they give you the input values, and they give you what the function is. For example, for a, it's x minus 4. And then they want you to find what the output is. So we can plug in our values, basically use substitution, and solve, x minus 4, where x is 4, and carry on through each of the values. And we're going to do the same thing for b, where it's 3 times x. Go ahead and do those, and I'll come back with the answers. Pause now. Now to start, the first thing I like to do is for the table, I like to fill in all my values that I automatically know. So I know it's all going to be minus 4, minus 4, minus 4. And over here I know it's going to be times 3, times 3, times 3. So then I can use a different color here, because you know how colorful I like to be, and I can fill in what the x values are. So we've got 4, we have 7, and we have 10. And over here we have 0, 2, and 5. And this way we don't mess up when we're bringing down the equation, because I will tell you that it does sometimes happen. Okay. So for A, we've got 4 minus 4, which is 0, 7 minus 4, which is 3, and 10 minus 4, which is 6. And for B, we have 3 times 0, which is 0, 3 times 2, which is 6, and 3 times 5, which is 15. And so there are our answers. It's just that easy. Now I'd like to do an example where we take this just a step further, since we're going to be needing to know this information later anyway. And I'm going to show you how we can also graph this information by adding another box here. So let's add another box. Now over here it's going to be kind of a funny little box. I don't have any room. So we're going to have a column for our x comma y, our ordered pairs. And so my ordered pair here, my x value is 4, my y value, which is my output, is 0. My x value is 7, and my output value is 3. My input value is 10, my output is 6. And then 0, 0 here, 2, 6, and 5, 15. And just, oops, sorry, that looks horrible. I'm just giving you kind of an introduction to that because we're going to be using that in just a moment. So I just wanted to point that out for you. Alright, so it wanted us to find what the independent variables were for example number 1. And I was going to have you answer below, but I've pre-filled in the answer for you, unfortunately. So you should see that 10, 12, and 14 are the independent variables because these are our input values. These are our x values. Okay, so 10, 12, and 14 from example number 1 are our input x values, which are also our independent variables. Now it says to find the input for a function table. Input and output of a function table can be represented as a set of ordered pairs, which I just kind of gave you a preview of, or a relation. So in this lesson, the x values represent the inputs and the y values represent the outputs. So x is going to be input, y is going to be output, which is what I just kind of mentioned to you. I have a little trick for remembering that I'm about to show you. Let me just give you a forewarning that if you use this incorrectly in school and a teacher overhears you or your parents don't like this because it could be taken the wrong way, I'm just pointing out there that this is your responsibility to be, big kids and make sure that you don't use this inappropriately. It's just something that I have found the kids remember a lot easier. So I'm going to put this on in just a second here, and I'd like for you to copy the note. Alright, so I call this table Dixon-Roy. We've got DIX, where our I and our X are our input and our X value. And then we have Roy, where the O and the Y stand for our output and our Y value. So like I said, we have to be mature about this. It's called Dixon-Roy. The reason I call it Dixon-Roy is because in 7th or 8th grade, you will learn what the D and the R stand for. This is actually, and you're not going to use this anytime soon, but I'm going to let you know what it is so you don't think I'm just making up dirty words. Domain, and this will be called range. Okay, so that's why we've got Dixon-Roy, because we've got I goes with X, and it also goes with domain, whereas O, our output, goes with Y, which is also goes with range. And you'll learn that later, the domain and range part, but for now, input and output. The input goes with X, that's our X, and then the output goes with Y, that's our OY. Okay, so Dixon-Roy, and that's just a little trick for you to remember it. Alright, you're going to do example number 3. I just wrote a couple little notes on here. Remember that when it says use the work backwards strategy, they're talking about the inverse operations, how to undo another operation to determine the input, and if the output is found by multiplying by 3, then the input is found by dividing by 3. Inverse operations, multiply, that means divide. So they're giving you the output values, they're giving you the relationship between X and Y, and you just have to plug it in. So the first thing that we do here, whoopsie, sorry about that. The first thing that we do here is we take our output, 6, which is our y. And we're going to say, okay, well 6 is going to be equal to 3 times x. And actually, I like to write this the other way around, so I'm going to fix this. 3 times x equals 6. So we know how to solve this. We've done our one-step equations already. So we know how to solve for x here. We need to do our inverse operation. Divide by 3, divide by 3. That leaves us with just x. And 6 divided by 3 is 2. So I find out that my value for x is 2. That means my output value is 6. And if I want to check that, I just plug it in to this equation. And I've got 3 times 2 is 6. Check mark. The next one now we're saying that 3x equals 15. So again, I'm going to do my t-chart here. I'm going to do my inverse operation by dividing by 3. I'm going to get x equals 5. So I'm going to add in my 5. I'm going to see 3 times 5. Does that equal 15? Check mark. Yes, it does. And so now I'm doing my 3x equals 21 for my last one here. I divide both sides by 3. I get x equals 7. When I'm checking my work, I'm going to say, okay, that's 3 times 7. Does that equal 21? Yep, it sure does. And so I find out that my input values are 2, 5, and 7 to go with my output values, which are 3, 15, and 21. Now you're going to do the examples for C and D on your own. And when you come back, I'll show you the answers. So please pause the video now and work on C and D. Alright, and here are the answers for C and D. I set them up the same way as I had that last example where I set up my equations and I substituted in for my x value. I set my output up as my y value, the answer to my relationship. So 2x minus 1 equals 1, 2x minus 3 equals 3, 2x minus 1 equals 3, 2x minus 1 equals 5. And I'm solving each of those by adding 1 first to both sides of the equation and then dividing by 2. For D, I did the same idea. For these, I need to subtract by 2 on both sides of the equation and then divide by 3. And my third one's right down here. I had to kind of smush it down here. And there's your answers. For number 4, it says the Gomez family is traveling at a rate of 70 miles per hour. The function rule that represents the situation is 70x, where x is the number of hours. Make a table to find how many hours they have driven at 140 miles, 280 miles, and 350 miles. So again, they're giving us the output values. They're giving us the output values, and we needed to figure out what the input values are, which they already did for us. So they said, okay, well, if it's 170 times x equals 140, then that's going to be 2. Because I'm going to do 140 divided by 70, and the answer is 2. I do 280 divided by 70, which is 4, and then I do 350 divided by 70, and that's 5. And so my chart says that when it goes 2 hours, that I've gone 140 miles. When I've gone 4 hours, I've gone 280 miles. And when I've gone 5 hours, I've gone 350 miles. And so you see that your hours down here represents your x value. See our x value? And that our distance in miles represents our y value, like we have over here. And so when it's been 2 hours, I go up to 140. When I go over 4 hours, I go up to 280. When I go over 5 hours, I go up to 350. And that's how we would graph the function. And so as you see, as we went, you can pretty much predict what the next one would be because you just add, after another hour, you've gone 70 more miles. Another hour, you've gone 70 more miles. And it would keep going on at a steady rate. Alright, now you're going to do E and F, and E says Brianna bikes 12 miles per hour. The function rule that represents the situation is 12x, where x is the number of hours, make a table and find how many hours she has biked when she has gone 12, 36, and 48 miles, and then graph the function. So I need you to figure out where you need to put all these numbers and solve for the missing numbers and then graph it. So when you come back, we'll go over those. All right, so you see here I've submitted everything into my table. I first set up my outputs, which were 12, 36, and 48. Then I set up my tables, my equation 12 times x equals 12, 12 times x equals 36, and 12 times x equals 48. I solve for x on each of those by doing the inverse operation, dividing by 12, dividing by 12, dividing by 12, and I get x is 1, x is 3, and x is 4. So when Brianna has biked 1 hour, she's gone 12 miles. When she biked 3 hours, she went 36 miles. When she biked 4 hours, she went 48 miles. And hopefully that makes sense to you if your table did not come out the same way. All right, now when we go to graph it, we're going to go over, over 1 hour and up to 12 miles because we've got hours here for x, distance here in miles. So then for 3 hours, we went up to 36. Then for 4 hours, we went up to 48. And of course, they're not exactly on the lines, so you're just kind of, fudging that a little bit. But if you kind of get the look of it, you can see that this is going to go in a nice straight line. Sorry, let me show that. Kind of a nice straight line. I know that doesn't look like a very straight line, but it is. And so that you know that 1 more hour, she's going to go 12 more miles. Another more mile, she'll go, another more hour, she'll go 12 more miles. And this is a steady pace that she's going. All right, so that is the end of 8.1 function tables. I will see you in school.